This presentation is about an introduction to dynamic programming, and my name is Karen Chen. Okay, so this is the outline of my presentation. First, I'm going to mention the principle of dynamic programming. Then I'm going to show you the four applications for this dynamic programming. Then I'm going to tell you the other representative dynamic applications which I'm not able to cover in this presentation. Finally, is the summary. Okay, the principle of dynamic programming is breaking down a complex problem into a collection of simpler subproblems. And to obtain an optimal performance of dynamic programming, we solve each subproblem and store their solution. So this is called memorizing or memorization for later use, which is considered to be more efficient than the brute force methods, which solve the same subproblems over and over again. So the first application of dynamic programming is in calculating the sum of mathematical sequence. So here, this is the original problem. Sum of n equals 1 plus 2 plus 3 plus etc. Until we reach n minus 1 plus n. And now we want to convert this original problem into a subproblem. So we group this n minus 1 items as sum of n minus 1 plus this n here, if n is greater than 0. And then this is the iterative. This slide shows you the difference between the iterative versus dynamic programming implementation about the sum of mathematical sequence. So on the left-hand side, this is the iterative programming, while the right side is the dynamic programming. So for this iterative programming, sum of n, sorry, we say results equals 0 for I equals 1 to n. Result equals result plus I, return results. And the time cost for this is big theta n. Then for dynamic programming, if we want to find the sum of n, we said if n equals 0, return 0, else return sum of n minus 1 plus n. And again, this time complexity or time cost is big theta of n. Then the second application of dynamic programming is Fibonacci sequence. And this sequence is created by Leonardo Fibonacci, which is used to calculate the population of rabbits. Okay, so here is the computation of Fibonacci sequence. Fn equals 0 if n equals 0. Fn equals 1 if n equals 1. Fn equals n minus 1 plus f n minus 2 if n is greater or equals 2. And this is solved by a recursive program. So here you will see this is consistent with the dynamic programming because we have convert the problem Fn into Fn minus 1 plus Fn minus 2. Or sometimes we will just say Fn1 plus Fn2 if n is equal or greater than 2. Then this is the difference between the recursive and the memorizing dynamic programming for Fibonacci sequence. So on the left-hand side, this is the recursive dynamic programming. So fib of n, if n equals 0, return 0. If n equals 1, return 1. Otherwise, just return fib of n minus 1 plus fib of n minus 2. And the time cost for this recursive dynamic programming is big O of 2 to the power n. Then on the right side here is the memorizing dynamic programming, so which starts with fib of n. If n equals 0, return 0. If n equals 1, return 1. If fn1 equals 0, fn2 equals 1, then sorry, no if. The here is fn1 equals 0, fn2 equals 1. For I equals 2 to n. Then fn equals fn1 plus fn2. Fn2 equals fn1 while fn1 equals fn. Then finally we return fn. And this memorizing dynamic programming is time cost is big theta of n. So you see this would be like faster than this memorizing dynamic programming is faster than the recursive dynamic programming. Okay, then now I just want to show you this slide. In this slide, how we can calculate the time cost for the recursive implementation of Fibonacci sequence. So I use the substitution method. So if we go back, or if you have questions, I can try to present in the class for this. And I may just skip here in this video. Then the third application of dynamic programming is Hanoi Tower. So in this Hanoi Tower, we move the entire stack to another row, obeying the following rules. First rule is only one disk may be moved at a time. And the second is no disk may be placed on the top of a smaller disk. Here I use a 3-disk Hanoi Tower as example. And if we have 3 disks at the route S, so S here is source, A is auxiliary, and then D is destination. So if we have 3 disks at the source spot, our source place, we want to move this to the destination. So how are we going to do that? So first, we move the top disk from S, from block S, to D, destination. Then we move the middle disk from S to A here. So now we move this the disk from D to the top of A. Then now we have this the last disk left. Then we just move it to the destination. And then now we move the smaller disk in A, from A to S. And then move this medium disk from A to D. Then finally, we move the smallest disk from S to D, right? So here we have 3 milestones. So milestone 1 is including these steps, and milestone 2 is the action of moving the last disk from S to D. And then milestone 3 is we move the n-1 disk to destination through S here. So I'm going to explain more in the next slide how this works out. So now this is a general case for N disk of Hanoi Tower. Okay. So the milestone 1 here is we move n-1 disk from S to A through D. So you will see here. So we move n-1 so is from the first, second, third, the 3 disk here. The first 3 disk, we move that to this. We move this to A. Then, but we move this to A is through this destination. Then we move the last disk from S to D, the destination, right? Okay, then so this first step, moving n-1 disk from S to A through the destination is called milestone 1. And then the action move the disk N from source to this destination is milestone 2. And then milestone 3, we move this n-1 disk from A to destination through this source. All right. So for the time complexity for this milestone 1, so it's T n-1, right? And then the time cost for this milestone 2 is only one operation, moving the last disk to the destination. Then this is 1, the time cost. And then milestone 3, moving this n-1 disk from A to D through this S. The time cost is T n-1. Okay, so here is the code or the dynamic programming implementation for Hanoi Tower, and I have explained in those 2 diagrams. And here are the steps I use to calculate the time cost for Hanoi Tower, and I use the substitution method. And then I found the time cost for this Hanoi Tower, the time cost using this dynamic programming to solve this Hanoi Tower is big theta 2 to the power of n+1. All right, so if I have the time to present this presentation in the class, I will let you do an in-class exercise to write a dynamic programming function to find the height of a binary tree. And the height here means the total number of nodes in the binary tree. And if I don't have the time to do this, then I have also provide a solution here. You can find the solution in the bottom here in this. All right. Then the fourth application of dynamic programming is used so dynamic programming can be used to find the longest common sequence between 2 DNA strings. So here, I assume, so suppose we have 2 cancer patients, and then this patient X and patient Y, and then patient X has a sequence of X, which has like a sequence of genes, or here I just use the symbols or characters to represent the gene sequence in X, sequence X. And then for sequence Y, for this patient Y, we have another DNA or gene sequence. Then if we want to find the longest common subsequence, just by looking at this, X equals this A, B, C, B, D, A, B. And Y have a sequence including B, D, C, A, B, A. Then how do we find the longest common sequence? So we probably, so we cannot change the order of these DNA sequence. So probably we would say, okay, so in sequence X, we have BCBA. And then in sequence Y, we can also find BCBA. And probably this is the longest common sequence for this for the cancer. Then but how do we how do I say, if I ask, so how do we find this out using a dynamic programming method? All right, so then I'm going to skip to slide 19 to see the longest common sequence algorithm. So, I may skip some of the slides in this presentation, but I will. But the content or information of those skipped slices would be covered when I use a 2D array to demonstrate the dynamic programming in finding the longest common sequence of two DNA strings. All right. So probably I will just show you that the 2D array first. So would we, in this longest common sequence algorithm, we would use this 2D array to show you how this dynamic programming works out. All right, so let me go back to slide 19. So in this longest common sequence algorithm, first we will find the length of longest common sequence, or I would just say LCS in short. Then later we will modify the algorithm to find the LCS itself. So first we find the length of LCS. Then we find out the sequence, the actual sequence itself. Okay. All right. So let's skip to see the longest common sequence recursive solution. Okay. So here C is the size of the actual the matched sequence we find in a 2D array. And then for I here, I is the index of visited gene or symbol in sequence X, and J is the index of visited gene or symbol in sequence Y. And when we calculate Cij, we consider two cases. So the first case is if Xi equals Yj. So means if these two gene or two symbol is the same, then the value of current cell in a 2D array equals is the value in the value of its upper diagonal cells plus 1. Otherwise, it's the second case then. If Xi doesn't equal Yj, then means the symbols they are not matched. So our solution is not improved, and then the length of longest common sequence of Xi and Yj is the same as before, and then so we just find the maximum value between the value in the j minus 1, so is in the above, and in the above cell, and also the value in the cell left to the current cell, right? Okay. So you may not get this until you see the 2D array. So let's, but I'm going to show you the whole LSC length algorithm first. So to find the longest common sequence is length for sequence X and sequence Y. First, we set m equals the length of sequence X, n equals the length of sequence Y. And for I, so I is the rows. For I equals 1 to m, C I 0 equals 0. J equals 1 to n, C 0, and J equals 0. For I equals 1 to m, for J equals 1 to n, if Xi equals for Xi if Xi is equivalent to this Yj, then we know the value of current cell equals to the value of its upper diagonal cells plus 1, else the value of Cij equals the maximum value of the above cell and the left cell. And then we return the length C. Okay, so here I will use an example to show you how longest common sequence algorithm works. So I suppose we have a sequence X, which includes these symbols A, B, C, B. Sequence Y includes symbols B, D, C, A, B. So what is the longest common sequence of sequence X and Y? So let's look at the 2D array. All right. So before we start to find a match, if J is 0, so it means we didn't have we haven't find any symbol in this sequence Y, then we will add all zeros here in this column. And then for if I equals 0, so means we didn't visit any symbols in sequence X. So then all this, the value for all this row is 0, right? So that means we haven't started to find a pair to check if they are the matched sequence. All right. So then if we look back to the code, starting from for I equals 1 to m. So we have explained that for I equals 1 to m, Ci 0 equals 0. And then for j equals 1 to n, the value for C O j equals 0. Then now, starting from 9, 5, for I equals 1 to m, for j equal 1 to n, if xi is equivalent to this yj, then we increment the value of its upper I mean here we how to say so for j equals 1, I equals 1, because check xi and yj, are they the same? They are not the same. So if they are not the same, then we need to find the maximum value between this among the value in the left cell and also the above cell and the left cell. Okay, so see, xi is not equals yj because a is not b. So then we have to find the maximum value between these two. So they are both 0. So we write 0 here. The next one. Next one, okay. Next one is B and A. Are they the same symbol? No. So then we find the maximum value between these two values. They are all the same 0, so we write a 0 here. Then for A and C, they are not the same symbol. So we find the maximum value between these two, and they are both 0, so we write a 0 here. Then next is A and A. This time xi is equivalent to yj. So what do we do? So we are not finding the maximum value between these two values. We are going back to, let's go back to see the code. If xi is equivalent to yj, then we need to increment the value in its upper diagonal, the upper diagonal cell by 1. Right. So here, A and A, they are both equivalent gene, and so they are matched. So now we increment the value in its diagonal, upper diagonal here by 1. So it's 0 plus 1. So we write down a 1 here. The next is A and B. They are not the same. So we need to find the maximum value between these two. So the maximum value is 1, right? Okay, so next row, B and B, they are the same symbol. So we have to increment this value 0 by 1. Then next one, we have the next 3 are D, C, A. They are all not the same as B here. So then we have to find the maximum value between these two values. So the maximum value of these two is 1, and the maximum value of these two is 1 again. Maximum value of these two again is 1. And finally, we find B and B here. So B and B, they are the same. So now we have to increment the value in its upper diagonal cell by 1. So 1 plus 1 is 2. Then next round, we have C in sequence X and B and D in sequence Y. So since B is and D, they are not the same as C, so we have to find the maximum value between these two values, which is 1, and between these two values, which is 1 again. Now we have C and C. So because they are the same symbol, so we have to increment the value in its upper diagonal cell by 1. So 1 plus 1 equals 2. And then the next two sequence in the next two symbols in sequence Y is A and B. They are not the same as C. So we are not going to do the increment. Instead, we find the maximum value of these two. So 2 and 1, 2 is the maximum. So we write 2 here, and then for these two is 2 and 2, so the maximum value is still 2. All right, then now, next one, when I equals 4, we have x1 is equivalent to yj. They're both b. So we have to increment this 0 by 1 and then put 1 here. Then the following three symbols in sequence Y, they are not the same as B in sequence X. So we will find the maximum value between these two is 1, so we put 1, and the maximum value between these two is 2. The maximum value between these two is 2. All right, so at the last, we find B in sequence Y. So this B is the same as B in sequence X. So we increment this 2 by 1 to get 3. Right. So this indicate the longest common sequence is 3. All right. So what's the longest common sequence algorithm's time cost or time complexity? So we know the longest common sequence algorithm calculate the values of each entry of the array C of M and N. Then what is the running time? So the running time for this is big O M times N. All right. Okay. So far, we have just found the length of the longest common sequence. But how about the actual longest common sequence itself? So to do this, we have to start from this array C MN and go backwards. So when C ij equals C I minus 1, j minus 1 plus 1, we need to remember this xi. until we reach the beginning, which is I equals 0 or j equals 0. Then we output the remembered letter in reversed order. So here, so if we go back from 3 to 2 to 1 and to 0, and we find when there's an increment of value by 1, we circle that symbol. So this is increment by 1, 3 here. So we circle this B and circle this B, and then there's the increment to get this 2. So we circle this C and this C. Then also we have another increment here. So we circle this B and B. So now we have found the reverse order of the longest common sequence. Then we know the strict order is also BCB. So in this case, this string turned out to be a palindrome. Okay. All right. So now, can you try to find the longest common sequence from the following 2 DNA strings? So if I have a chance to present this presentation in the class, then I will let you practice it. And then there are other representative dynamic programming applications like 0-1 knapsack, shortest path in graph, and optimal search of binary tree. But due to the time limitation, I cannot cover all these topics in this presentation or in the class. And so this is the summary of dynamic programming. So dynamic program can solve a lot of complicated problems. And the key is to convert a complex problem into a collection of simpler subproblems. And then in order to improve the performance, we will memorize the solution to these subproblems for later use so that we can avoid some redundant operations. Okay, and here is the reference. Then it's the end of my presentation. Thank you.